Hello my friends and welcome back to the You Can Do TV channel. At Newport News Shipbuilding in Virginia, a monumental task unfolded to create the USS Gerald R. Ford, CVN-78, the lead ship of a new class of aircraft carriers. This was no ordinary construction project. It was a bold endeavor to craft the Navy's most advanced warship, blending cutting-edge technology with a legacy of leadership. The process, from initial concepts to commissioning, was a symphony of collaboration, ingenuity, and dedication, engaging thousands of shipbuilders, engineers, and designers to transform a vision into a floating fortress. The journey began with a blank slate when the project, initially known as CVX, was just an idea. Engineers and designers huddled in modest cubicles, tasked with imagining a carrier to serve for half a century. The challenge was daunting. Design a vessel that could adapt to future needs while meeting the Navy's rigorous demands. Would it be nuclear-powered, gas turbine-driven, or something else? The team explored countless compartment designs, iterating through concepts in a collaborative space where every suggestion counted. Using 3D modeling, they crafted a virtual papership, walking through digital compartments long before physical construction began. This digital foundation set the stage for a carrier that would redefine naval aviation. The aircraft carrier reached a pivotal milestone with the final superlift, completing its primary structure. This last of 162 superlifts, hoisted by the massive crane, marked the end of extensive structural erection. Newport News shipbuilding became a hive of activity. Over 23,000 shipbuilders, welders, pipefitters, electricians, and sandblasters worked in harmony, each contributing to a vessel the length of 3 football fields. The process was a delicate dance, blending veteran expertise with the training of newcomers. The shipyard invested in advanced facilities, including a massive crane and specialized fabrication bays, to handle the carrier's enormous components. Hundreds of base units were built, each piece precision crafted to endure decades at sea. The precision lift, a testament to the shipbuilder's skill, united the nuclear-powered carrier's framework, setting the stage for outfitting and testing. Each superlift reflected years of dedication, bringing the Navy's most advanced warship closer to its mission-ready future. A pivotal moment came when global events underscored the urgency of a strong defense. The team, galvanized by a renewed sense of purpose, shifted into high gear. Declared a nuclear-powered carrier, and later named the USS Gerald R. Ford, after the 38th president, a man of integrity and service, the project gained momentum. Construction started with the cutting of steel, marking the transition from concept to reality. The keel-laying ceremony followed, a symbolic milestone that anchored the ship's future. The Ford-class aircraft carriers feature innovative flexible spaces designed for adaptability. These spaces allow rapid reconfiguration to meet evolving mission needs, enhancing operational efficiency. At Newport News Shipbuilding, apprentice school students demonstrate this capability in a flexible lab space, swiftly rearranging modular components to simulate different configurations. This design philosophy ensures the carrier can accommodate new technologies, crew requirements, or tactical demands without extensive retrofitting. By prioritizing versatility, the Ford-class carriers remain future-proof, ready to serve for decades, while maintaining peak performance in dynamic naval operations. As a prototype and production model rolled into one, the Gerald R. Ford introduced revolutionary technologies, like the Electromagnetic Aircraft Launch System, EMALS, which replaced steam catapults with a smoother, more efficient mechanism. Integrating these systems was no small feat. Unlike an airplane prototype, there was no test model. Every weld, wire, and system had to be flawless from the outset. Shipbuilders tackled challenges, from aligning new structural steel to applying corrosion-resistant coatings in hidden areas like the jet blast deflector pits. Sandblasters, the unsung heroes, ensured these compartments would last the ship's 50-year lifespan. Key milestones punctuated the process, each a moment of collective pride. The placement of the island, the carrier's control tower, was a landmark event, with Susan Ford Bales, the ship's sponsor and President Ford's daughter, placing her naval aviator wings beneath it. The flooding of the dry dock brought the ship to life as water met its hull for the first time. The christening ceremony saw Susan Ford Bales break a bottle across the bow, declaring, "May God bless this ship and all who sail her." Sea trials tested the ship's limits, from high-speed maneuvers to emergency anchoring, ensuring it could handle decades of service. The shipbuilders' pride ran deep. From veterans who shaped early designs to newcomers awestruck by the carrier's scale, each felt a personal connection. Susan Ford Bales, an engaged sponsor, worked alongside them, pulling cables and shaking hands, embodying her father's hands-on spirit. When the USS Gerald R. Ford was commissioned, it stood as a city at sea, ready to serve. For the shipbuilders, it was a dream realized, a testament to integrity, craftsmanship, and innovation, built to defend freedom for generations. The construction of the sail training ship Unión by Cima, Peru, represents one of the most ambitious shipbuilding projects in the country's recent history. Designed as a modern training platform for the Peruvian Navy, the Unión combines traditional craftsmanship with advanced naval engineering. The process is being carried out in phases, beginning with the modular assembly of the ship's structure, integration of critical systems, and culminating in the outfitting and final commissioning. The construction process follows a modular block methodology, a widely adopted approach in modern shipbuilding. This strategy allows different parts of the ship to be built simultaneously and later assembled with high precision. A total of 38 blocks will form the complete structure of the Unión. As of the current stage of development, 29 modules have already been successfully constructed. These include essential components such as the accommodation sections, the engineering plant, and the double bottom. Elements that contribute to the vessel's foundational stability, operational safety, and long-term durability. Each of these modules was fabricated separately, involving precision cutting, welding, and structural alignment to ensure seamless integration. Once completed, the modules were transported and assembled within the dry dock using heavy-duty cranes and positioning systems. The double-bottom sections were among the first installed, offering a critical watertight base and serving as structural support for additional systems and load-bearing components. parallel to the assembly of the initial 29 modules, SEMA Peru has been working on 9 additional blocks. These are primarily focused on the stern and central deck areas, which include structural reinforcements and specialized framework for masts, rigging bases, and navigation systems. These blocks demand increased attention to weight distribution and internal space optimization, as they will house vital systems and form part of the ship's operational deck. The engine room, one of the most complex sections of the vessel, has seen substantial progress. Approximately 70% of the machinery and equipment required for this area has already been installed. This includes the main propulsion engines, onboard diesel generators, air conditioning units, and various auxiliary systems. The installation of this equipment within pre-assembled modules pose logistical challenges, requiring detailed coordination between design engineers and mechanical teams to ensure accurate placement, secure mounting, and connectivity for future operations. To support the vessel's propulsion, the main engines were carefully installed on vibration-dampening foundations and aligned with the propulsion shafting. Generators were placed with access for future maintenance and wired to the ship's power distribution systems. Air conditioning systems, essential for habitability and operational performance, were also installed with routing for ductwork and integration into the accommodation modules. The outfitting process, which continues as modules are joined, involves the installation of piping systems, cable trays, HVAC ductwork, insulation, lighting, and safety equipment. All systems are carefully tested for pressure, alignment, and connectivity before final closure. Integration of electrical and control systems has been ongoing, including the installation of control panels and power distribution boards. Special attention has been given to habitability and crew welfare during the outfitting of accommodation blocks. These areas are being equipped with bunk spaces, mess halls, restrooms, study rooms, and leisure areas. Materials used in these spaces are selected for durability, ease of maintenance, and comfort. The air conditioning system ensures a stable indoor climate across different compartments, particularly important during extended training voyages. Safety systems, such as automatic fire suppression, alarm systems, and emergency lighting, are being embedded within the vessel. Escape routes and emergency exits have been designed to meet international safety standards. Integration of fire detection systems and watertight doors is carefully monitored to ensure compliance and operational reliability. The ship's masts, spars, and rigging infrastructure will be installed in later stages, following the completion of the hull structure and the launch. These will include heavy-duty sailing rigs, booms, and deck winches, essential for cadet training in seamanship and traditional navigation. Reinforced areas within the deck blocks are already being prepared to receive the base structures for these components. Safety systems, such as automatic fire suppression, alarm systems, and emergency lighting, are being embedded within the vessel. Escape routes and emergency exits have been designed to meet international safety standards. Integration of fire detection systems and watertight doors is carefully monitored. Radar, communications, and seamanship simulators will be installed and tested prior to commissioning. From a technical standpoint, the Union's propulsion and power systems are being designed to offer high reliability, operational efficiency, and reduced emissions. The machinery spaces are configured to provide good accessibility for operation and maintenance, as well as to minimize noise and vibration throughout the living quarters. Sustainable technologies, such as efficient fuel usage systems and onboard energy management, are being integrated to reduce the vessel's environmental impact during deployment. Once all structural blocks are fully assembled and outfitted, the vessel will proceed to launch. This crucial stage will involve transferring the complete hull from dry dock to water using synchronized cranes and supports. The process will be carefully executed to prevent structural stress or damage. The christening ceremony will follow shortly after the launch, marking the vessel's formal introduction and blessing before beginning its sea trials. Post-launch operations will include harbor trials, calibration of navigational systems, and safety checks. This period is crucial for validating the performance of propulsion, steering, communication, and life-saving systems. Sea trials will then be conducted to assess the ship's handling, speed, maneuverability, and endurance under operational conditions. These tests will ensure that all systems are fully functional and that the vessel meets the specifications set out in the design. Throughout the construction process, SEMA Peru has adhered to rigorous quality control and inspection procedures. Each phase is subject to oversight by naval inspectors, classification society representatives, and engineering supervisors. Welding joints, steel grades, painting systems, and system installations are all documented and verified to ensure the vessel's compliance with naval and international maritime standards. Ships needing repairs at Asyad Drydock are brought into dry dock, where ships are positioned in one of two dry docks capable of accommodating vessels up to 600,000 DWT. Once secured, inspection teams conduct a comprehensive assessment to identify required repairs. Sandblasting and hull painting are carried out to remove corrosion and restore protective coatings. Simultaneously, mechanical and electrical teams begin repairs on deck machinery, RORO equipment, cranes, and stuffing boxes. CNC, oxygen, and plasma cutting machines are used for precision metalwork and structural repairs. Damaged components are either repaired or replaced using in-house fabrication and machining capabilities. For offshore platforms and heavy industrial structures, custom steel fabrication and welding services are provided. Electrical systems are tested and overhauled to ensure full functionality. Upon completion, the vessel undergoes final inspections, followed by flooding of the dry dock and undocking. The Olympic trophy is a remarkable example of successful maritime vessel conversion, transforming from a very large ore carrier, VLOC, into a very large crude carrier, VLCC, in just 51 days. This ambitious project was executed at the Oman Drydock Company shipyard in Duqm, highlighting the facility's growing reputation for complex and high-precision ship conversions. Originally designed to transport massive quantities of iron ore, the Olympic trophy underwent extensive structural and systems modifications to meet the stringent requirements of crude oil transportation. The conversion involves significant engineering works, including alterations to the cargo tanks, installation of new pumping and piping systems, and reconfiguration of ballast systems to comply with VLCC specifications and international maritime safety standards. The entire operation demanded precise planning, a high level of technical expertise, and seamless coordination between design engineers, project managers, and shipyard workers. Completing such a complex transformation in just 51 days not only underscores the capabilities of the Oman Drydock Company, but also sets a benchmark for future conversions of large vessels. This successful project has positioned Duqm as a competitive hub for advanced ship repair and conversion services in the region, attracting more attention from international shipping operators looking for efficiency, quality, and turnaround speed. In this episode, You Can Do TV will take you to at the Pinamarin shipyard at Antalya Free Trade Zone, Turkey, to discover how full aluminium catamaran is built. First, the design and engineering phase is crucial, where naval architects and engineers collaborate to ensure the catamaran will meet specific performance and safety requirements. Aluminum is chosen for its strength-to-weight ratio, corrosion resistance, and ease of fabrication, making it an ideal material for both commercial and recreational vessels. Once the design is finalized, the next step is the cutting and shaping of aluminum plates and beams. Precision is key in this stage to ensure all parts fit together perfectly during assembly. Modern technology like CNC machines and laser cutters is often used to achieve highly accurate cuts. The aluminum plates are then welded together using advanced welding techniques such as TIG, tungsten inert gas welding, which is ideal for aluminum due to its ability to produce clean, strong welds with minimal distortion. The next phase is the assembly of the two hulls, which are the primary components of the catamaran. These hulls are constructed separately and then joined by cross beams that support the structure. The alignment of the hulls is critical to ensure optimal balance and stability on the water. After the basic structure is in place, the catamaran is outfitted with various systems, including electrical wiring, plumbing, and the engine setup. The deck and interior spaces are designed to provide comfort and functionality, with the use of lightweight yet durable materials for flooring, furniture, and storage. Finally, the catamaran undergoes thorough testing to ensure that it performs well under different conditions. Sea trials assess its stability, speed, and maneuverability. Once it passes these tests, the full aluminum catamaran is ready for launch, offering a vessel that is both high-performing and built to last. The 66-meter Shadow Yacht Hodor carries an impressive toy box, a 55 feet Nortec tender Fancy Sauce, 43 feet Skater Regal, 26 feet Centurion Wake Surfboat, 28 feet Landing Craft, SE Imagine Submarine, 6 jet skis, a full dive center with nitrox and decompression chamber, plus numerous off-road and water toys. Over the past 15 years, large steel shipbuilding technology, particularly block construction, has advanced significantly, enhancing efficiency and precision. Block construction involves prefabricating large sections, blocks, of a ship's hull and superstructure, which are then assembled to form the complete vessel. This modular approach, widely adopted since the early 2010s, has reduced construction time by 20 to 30% compared to traditional methods, with modern shipyards completing vessels in 12 to 18 months versus 24 to 36 months previously. Globally, shipyards like South Korea's Hyundai Heavy Industries and China's China State Shipbuilding Corporation, CSSC, have led innovations. By 2023, China accounted for 53% of global merchant tonnage, up from 14% in 2003, largely due to block construction advancements. Each block, often weighing 500 to 1,000 tons, is prefabricated with pre-installed piping, electrical systems, and equipment, minimizing on-site assembly errors by 15%. Advanced welding techniques, such as laser hybrid welding, have improved joint strength by 30%, enabling ships with capacities exceeding 400,000 DWT, deadweight tonnage. In Vietnam, the shipbuilding industry has grown rapidly, with 88 enterprises and a capacity of 2.6 million DWT annually by 2024. Hyundai Vietnam Shipbuilding, a joint venture, has built 199 vessels since 2009, becoming Southeast Asia's largest shipyard. Block construction adoption has enabled Vietnam to rank 7th globally, producing 0.61% of the world's ships in 2021. Investments in CAD/CAM systems and robotics have boosted precision, reducing material waste by 10 to 15%. Environmental considerations have also shaped technology. Since 2015, eco-friendly coatings and corrosion-resistant TMCP steels, e.g., EH36, EH40, have extended ship lifespans by 5 to 10 years. Vietnam's focus on green growth aligns with global trends, with shipyards like Ha Long Shipbuilding integrating hybrid propulsion systems, cutting emissions by 20%. These advancements underscore block construction's role in revolutionizing large steel shipbuilding, balancing efficiency, scale, and sustainability. The construction of the 66-meter Shadow Boat Hodor was a highly specialized process, combining innovative marine engineering and cutting-edge design to meet the demands of modern expedition-style yachting. Built by Astilleros Arman in Spain, Hodor was designed by Incat Crowther and outfitted by YCTS to function as a support vessel to a mothership, carrying an extraordinary array of toys, tenders, and equipment. The hull and superstructure were constructed entirely from steel and aluminum, ensuring durability, lightweight efficiency, and structural strength. Advanced modular construction techniques were employed to speed up the assembly process, with various sections prefabricated and then joined together at the main yard. Throughout the build, precision engineering played a crucial role to accommodate complex systems, like the custom-designed cranes and launch systems, needed for deploying multiple tenders and submersibles. The vessel features a heavy-duty catamaran hull for improved stability and increased deck space. This layout allows Hodor to carry a fleet of watercraft, including a 55-feet Nortec performance tender, a 43-feet skater, a Centurion wakeboat, a submarine, jet skis, ATVs, and more. Custom-made storage and handling systems were installed to ensure safe deployment and retrieval of equipment, even in challenging sea conditions. Interior outfitting included facilities for a dive center, complete with nitrox capabilities, a decompression chamber, and accommodations for up to 20 crew members. Hodor exemplifies the future of shadow yacht construction, combining robust capability with elegant design and seamless logistical support for global yachting expeditions. The construction of the Ada Nova at Meyer Werft began with the ceremonial keel laying, marking the placement of the first block into the dry dock. Following this, the ship's engine room module, essential to powering the vessel, was fabricated and precisely integrated into the hull. Next came the block construction of the first floating section, a part of the ship already capable of buoyancy, forming the foundation for further assembly. This was soon followed by the construction of the second floating section, which was later connected to the first, creating the basic shape of the vessel. Simultaneously, prefabricated passenger cabins were carefully hoisted and installed, each one fitted into its exact position within the structure. One of the major technical milestones was the installation of the propulsion systems. The azopod units were mounted first, followed by the massive propellers that would drive the ship. With all major structural and mechanical components in place, the ship was then floated out of the dry dock in a significant milestone on its journey toward completion. The final step was the Ems River conveyance, a precision operation in which the massive vessel was navigated through the narrow Ems River to reach the open North Sea, ready to embark on its maiden voyage. This is Spectrum of the Seas. It represents a major milestone in modern cruise shipbuilding. As the first ship of the Quantum Ultra class, she was designed to combine cutting-edge maritime engineering with state-of-the-art passenger experiences. The process began with the precision cutting of steel and the assembly of massive ship blocks, each meticulously fabricated and outfitted, before being joined together in the shipyard's covered building dock. The ship measures 347.1 meters in length and 41.4 meters in width, with a gross tonnage of 169,000 GT. She can accommodate up to 4,246 passengers, offering a wide range of luxurious staterooms, suites, and high-tech entertainment areas. Construction included the installation of innovative features, such as the North Star Observation Capsule, the Ripcord by IFLY Skydiving Simulator, and the Bionic Bar, where drinks are served by robotic bartenders. The Arleigh Burke-class destroyer, Ralph Johnson, DDG-114, underwent a complex 3-day translation process to dry dock in early December at Ingalls Shipbuilding. On day 1, the ship was carefully shifted southward in the operation known as South Move 1, aligning it with the river track to begin its path toward the dry dock area. This initial movement ensured that the vessel was on the correct trajectory for the next stages. Day 2 saw the continuation of the translation with a coordinated shift westward, gradually positioning the destroyer closer to the dry dock. This step required precise maneuvering and timing to ensure both safety and structural integrity during the move. On day 3, the final stage involved rallying the vessel at the jacks for the critical move and set operation into the dry dock itself. The ship was successfully positioned and stabilized, marking a key milestone in its construction and pre-commissioning process. Repair and maintenance operations at Oman Drydock Company, ODC, follow a structured and highly efficient process, supported by world-class infrastructure. Upon arrival, vessels are guided to one of the 44 berths along the 2,800-meter-long quays for initial inspection and preparatory work. Depending on the scope, ships are then transferred to one of the 2 dry docks, each measuring 410 meters in length, with widths of 95 and 80 meters, depths of 10 meters, and dock wall heights of 14 meters. These dimensions allow accommodation of ultra-large vessels for hull treatment, structural repair, and mechanical overhauls. Inside the dry docks, activities include blasting, painting, propeller and rudder inspection, replacement of steel structures, and machinery repairs. The 453,000 square meter yard reclamation area is utilized for heavy fabrication, pre-assembly of structural components, and storage of materials and equipment. Specialized teams perform diagnostics on engines, navigation systems, and auxiliary units using advanced tools and mobile platforms. Throughout the process, operations adhere to international safety and quality standards. Integrated logistics systems ensure timely delivery of parts and seamless coordination between teams. The yard's large footprint of 1.2 million square meters ensures simultaneous handling of multiple projects, enhancing throughput and efficiency in delivering comprehensive ship maintenance and repair services. Replacing a cruise ship engine without using the front door requires precision engineering and logistics. On the Norwegian Star, a damaged 90-ton engine block, located 6 meters below the waterline, was removed by cutting a hole in the ship's hull at a Rotterdam dry dock. After internal prep work, reinforcing floors and removing piping, the block was extracted. Coordinated by Man Energy Solutions with Damon and Mammoet, the engine was replaced with minimal service disruption, despite COVID-19 challenges. Final commissioning of the new engine was handled on board by Man Prime Serve. Ships, like all machines, eventually reach the end of their operational life, typically after 20 to 30 years. When that time comes, responsible recycling is essential. Over the next decade, more than 15,000 ships are expected to be dismantled, presenting a major opportunity to improve global practices. Choosing certified recycling yards that comply with international standards, such as the Hong Kong Convention, is crucial to protect both workers and the environment. Recycling ships not only recovers valuable steel, but also supports the circular economy. Safe and environmentally sound ship recycling is no longer optional. It is an urgent need. Unified global action, guided by shared regulations, is the only path to a more sustainable maritime future. The time for change is now. When a cruise ship, like the MSC Magnifica, arrives for repairs, the process is nothing short of a well-orchestrated engineering feat. Built in 2010 and stretching 293 meters in length, this grand vessel docked at Damen Ship Repair Rotterdam, one of Western Europe's largest dry docks, on October 20th. With only 17 days to complete all works, the Damen team faced a tight schedule and rose to the challenge. Before the MSC Magnifica even arrived, hundreds of dock blocks were positioned to support her hull once the dry dock was drained. Once in place, auxiliary engines kept running to support the 700 crew members who stayed aboard during the repairs. Scaffolding went up quickly, and work began on multiple fronts. Steelworkers replaced 40 tons of hull steel, while painters worked around the clock to coat over 6,000 square meters of surface. Simultaneously, the ship's rudder system underwent a complete overhaul. The original rudder stocks were removed, modified on site, and fitted with brand new rudders, precision work made easier by Damen's integrated facilities. Other teams inspected and serviced lifeboats and davits, cleaned and polished propellers, and repaired stabilizers and thrusters. The hull was coated in anti-fouling paint to enhance performance and reduce marine growth. Thanks to efficient coordination, advanced facilities, and non-stop effort, the MSC Magnifica was repaired, polished, and ready to sail, leaving Damen Ship Repair Rotterdam a day ahead of schedule, gleaming and fully prepared for her next voyage. Towering over the dockyard with unmistakable presence, the Norwegian Epic arrived at Damen Ship Repair Brest for a transformation as impressive as the vessel itself. This iconic cruise ship, known for its grandeur and size, was set to undergo a high-stakes refit and maintenance program that demanded speed, precision, and seamless coordination. Measuring 329 meters in length, the vessel received attention from over 3,000 specialists working around the clock to meet a tight deadline. Key operations included the fitting of 2 new rudders, overhaul of stabilizers, and exchange of diesel generators. 22 lifeboats were removed for servicing, while public spaces aboard the ship were refreshed to enhance passenger experience. The use of robotic ultra-high-pressure (UHP) blasting technology ensured efficient and environmentally conscious hull cleaning. Cooling water connections handled capacities up to 800 cubic meters per hour, underlining the technical scope of the project. With complex logistics and coordination across multiple teams, the project's success was a testament to Damen's integrated shipyard capabilities. Departing a day ahead of schedule, Norwegian Epic left Brest renewed and cruise-ready. The construction and maintenance of nuclear-powered U.S. Navy aircraft carriers is one of the most complex and resource-intensive industrial efforts in the nation. These vessels are built and overhauled primarily at Newport News Shipbuilding, the only U.S. shipyard capable of constructing nuclear-powered aircraft carriers. The process integrates thousands of suppliers across 44 states, making it a nationwide industrial effort. Construction begins with a modular build approach. The hull and superstructure are fabricated in sections or modules, often weighing hundreds of tons each. These modules are pre-outfitted with systems such as electrical wiring, piping, and insulation before being transported to dry dock for assembly. High-capacity cranes, including the largest in the Western Hemisphere, are used to lift and align these modules with precision. Integration includes major systems like the nuclear propulsion plant, catapults for aircraft launch, arresting gear for recovery, and advanced radar and communication arrays. Throughout the process, rigorous quality control and system testing ensure the integrity of each component. Critical systems like aircraft elevators, NATO Sea Sparrow missile launchers, and environmental controls undergo repeated adjustments and testing phases to meet exacting Navy standards. Interior outfitting also proceeds in stages, with spaces progressively turned over to Navy personnel as compartments are certified for operational use. Maintenance, especially through the Refueling and Complex Overhaul (RCOH) program, is equally detailed. This midlife overhaul involves removing spent nuclear fuel, upgrading combat and propulsion systems, and modernizing living quarters and command centers. The process strips the ship down to its structural core, after which it is rebuilt and recommissioned for another several decades of service. Tasks include reworking steam systems, realigning catapult tracks, and installing new electrical and electronic systems. Each RCOH requires precise coordination among hundreds of trades and is executed on a rigid timeline to ensure readiness. During both construction and overhaul phases, systems like fire doors, aircraft handling elevators, and de-icing wiper systems are tested for operational readiness under simulated conditions. From large-scale welding and painting to the installation of specialized equipment like anti-fog heaters and missile defense systems, each process step is vital to ensuring full mission capability. Material logistics are a continuous challenge, requiring synchronized delivery and inventory management between suppliers and the shipyard. This nationwide collaboration ensures a steady flow of parts, from structural steel to precision electronics. The coordination with suppliers is critical, especially for just-in-time components essential to keeping work on schedule. The work represents a combination of heavy industry, fine engineering, and sustained collaboration. As the vessels approach completion, attention shifts to sea trials and final certifications, marking the transition from construction to deployment. Each carrier thus stands as a testament to American industrial capability, technical skill, and collective commitment to national defense. The Federal Elbe, a bulk carrier, underwent a significant repair and maintenance project at MTG Dolphin Shipyard, located in Varna, Bulgaria. This project was part of the vessel's routine dry docking and inspection process, ensuring that it continues to meet international maritime safety and operational standards. Upon arrival, the ship was securely docked in one of MTG Dolphin's floating docks, where teams of skilled technicians and engineers began a comprehensive inspection and assessment. The scope of the repair included hull cleaning and painting, replacement of steel plates in corroded areas, maintenance of the propeller and rudder systems, as well as inspection and overhaul of ballast water treatment and cargo systems. Particular attention was given to the vessel's underwater hull to improve hydrodynamic efficiency and fuel consumption. Engineers also worked on various mechanical and electrical systems, including auxiliary engines and piping networks. All work was carried out in compliance with the vessel's classification society regulations and under close supervision to meet tight deadlines. Thanks to MTG Dolphin's expertise and advanced facilities, the Federal Elbe was returned to service efficiently and on schedule, ready for its next voyage with improved performance and reliability. The Montrose Bridge-Linked Platform BLP topside, developed for Repsol Sinopec Resources UK, marked a significant step in extending the life of the Montrose area in the UK North Sea. Constructed at the Hirema Fabrication Group's yard in Zwijndrecht, the Netherlands, the project commenced in March. Over the course of 3 years, the facility was fabricated and outfitted with advanced process systems, living quarters, and essential operational infrastructure to support continued production from the Montrose area fields. The BLP is a vital component of the Montrose Area Redevelopment MAR project, designed to provide additional processing and accommodation capacity. One of the key engineering challenges was its bridge-linked design, which connects it directly to the existing Montrose Alpha platform. This approach allowed for improved operational integration while minimizing environmental and logistical impacts. By April 3, years later, the topside structure was completed and readied for offshore installation. It was transported from the Zwijndrecht yard to the UK North Sea using a heavy transport vessel. The installation was executed using Hirema Marine Contractors' semi-submersible crane vessel Thialf, one of the largest of its kind in the world. The lift and installation operation required extreme precision due to the weight and dimensions of the structure and the close proximity to the existing platform. Successfully installed and commissioned, the Montrose BLP topside represents a milestone in offshore engineering and a major achievement in North Sea asset rejuvenation. It plays a crucial role in enabling Repsol Sinopec to maximize recovery from existing fields while reducing the environmental footprint associated with new infrastructure development.